Hello everyone, today I want to give you just a conceptual understanding of what Green's theorem is. We're not going to talk about how the formula per se works. We're just literally going to talk about what Green's theorem is finding. Therefore, you can have a better understanding of what it actually is. Because when I first learned Stokes' theorem, I was a little confused to say the least. It took me some time to actually understand what that was. So if you remember, work is equal to the force dotted with dr and along some curve C. Okay, so pretty simple. And that just says if I'm going through some vector field, right? Imagine there's all these little arrows pushing pushing against our particle or pulling our particle, right? A vector field, right? So that's what all those little yellow arrows were. Well, let's say we have a little curve and it goes like this, okay? So we start at this point on the xy plane and then we kind of curl up into this little point here, which is some point in space. Okay, the work is found by evaluating this integral. We know that. We've done line integrals. Okay, but imagine now that we have this specific kind of curve, okay? It's on the xy plane, so the xy plane, and it's simple and closed. And if you recall, what that means is that we can utilize this thing known as Green's theorem. And all Green's theorem said is for a simple closed curve, meaning it's fully continuous, it doesn't overlap itself, and it's closed, right? It encloses a space, right? We can redefine work to be a little different. We can say that work is equal to the double integral of the curl dA. Okay, so remember that's what Green's theorem said. If you have a simple closed curve, right, then the work is equal to the double integral of the curl. It's actually a pretty simple concept once you do it a couple times. However, what if instead we changed the curve? And let's say we just kind of lift up this, so that this edge here, let's say we kind of lift it up a little bit this way, right? So we kind of go from under and we lift it. It would look something like this, right? Hopefully you can agree. And it goes up and around, right? And just for clarity, right, this is lifted up. This little section, this is lifted, right, where this is just on touching the xy plane. So hopefully you can see what I'm trying to do there. But now the question becomes, does Green's theorem hold? Is this true? Okay, well the answer is no. Green's theorem, if you notice, the curl that you'd be evaluating is only in 2D. The curl of this curve would be d partial q partial x minus partial p partial y. But notice now that this curve is not in 2D, it's in 3D, so we have to have z components in there, and that's where Stokes' theorem comes in. It's this huge long theorem that we can find, but it basically says that the work, and we're going to see an extension of this idea, work is going to be equal to the double integral on a surface with the curl dotted with the normal vector, right? Just keep it, not the unit normal, just the normal, right? Because it turns out we have this other term here, but the magnitudes cancel out, so it's not needed. So this is literally Stokes' theorem. And it just says that the work done by a particle traveling through space is equal to this double integral where we have the curl dotted with the normal vector, right? So all we did is we took Green's theorem and we shifted it, right? You might also see that you're given a curve instead. Okay? right? So let's say we have this curve, the same curve, but let's say instead of just it being a circle, it's a little, hemisphere, right? So let me just kind of shade that in here. So we have a little hemisphere now. The property still holds true. The total flux moving through that object is equal to this, right? And the reason we can say that, and if I remember correctly, I'm not too familiar with this idea, that the curls at any point are going to cancel out. So let's say you have a positive curl here, completely next to it you'd have a negative curl, and they cancel out, except when you get to the boundary there's going to be some curls there. So we can look at it as work traveling among a curve. We can also look at it as the total flux of a surface if and only if there's a boundary to that curve that can be defined in the Stokes theorem. So hopefully that idea was helpful. If it was, please drop a like, comment, and subscribe. I greatly appreciate it. I hope that you have a wonderful day. Bye-bye.